Spanning tree. All right. What is a spanning tree? It's a subgraph that contains all of the vertices of the original graph, but with the minimum number of edges needed to keep the graph connected. For example, the graph pictured here is an example of a connected graph. However, I don't need every single one of these edges to keep the graph connected. If I were to get rid of these red edges right here, the graph would still be connected. Thus, the original graph is not a spanning tree. It's connected, but it's not spanning because it has more edges than necessary. This graph, however, right here that we're looking at right now, is a spanning tree because if I were to get rid of any one of these edges, then the graph would become disconnected. This graph is also not the only spanning tree for that original graph. This is also a spanning tree. A different set of edges, nevertheless, same set of vertices, and they're all connected. So it is possible for a graph to have more than one spanning tree. So, how do we go about generating a spanning tree from a given graph? To do so, we're going to perform a depth first search. We're going to perform the same steps, but with just one additional step. As we go from vertex to vertex, each edge that we traverse along the way, we're going to store in an array list. The edges that get stored in the array list over the course of this algorithm will be the edges we keep, and the edges that don't get put in the array list will get thrown away. So, let's begin. We'll go to our starting vertex. In this case, it'll be A. Then we'll mark it as visited. We'll push it on the stack. Then we'll go to an adjacent unvisited vertex. We'll go to C. So now we're going to mark C as visited. We're going to push it on the stack. Then the edge that connects A and C, we're going to add it to the array list. Next, visit an adjacent unvisited vertex from C. D is one of those. We'll mark it as visited, push it onto the stack. Then the edge that connects C and D, we'll add it to the array list. Next, visit an adjacent unvisited vertex, mark it as visited, push it onto the stack. Then the edge that connects D and B, add it to the array list. Next, visit an unvisited adjacent vertex, mark it as visited, push it onto the stack, and then the edge that connects B and E, add it to the array list. Next, visit an adjacent unvisited vertex, mark it as visited, push it onto the stack, then the edge that connects E and F, add it to the array list. Then, visit an adjacent unvisited vertex, mark it as visited, push it onto the stack, then the edge that connects F and G, add it to the array list. Now we see that G has no unvisited adjacent vertex, so now we're going to begin popping the stack. We're going to pop G from the stack, then use the peek method to return to the vertex we visited before that. F also has no other unvisited adjacent vertex, so we're going to pop F from the stack, then go back to E. Then we're going to pop E from the stack, return to B. Pop B from the stack, return to D. Pop D from the stack, return to C. Pop C from the stack, return to A. A has no other adjacent unvisited vertex, so we'll pop A from the stack, thus completing the algorithm. Right? And all the edges that were added to the array list we'll keep. All edges that were not added to the array list, we discard, thus completing the algorithm.